All right, I couldn't help myself. On the last problem, I worked it out in cylindrical coordinates as well, and definitely spherical coordinates was the way to go. It was significantly faster, but it was not bad in cylindrical as well. The U substitution worked just fine. Got a little messy with the signs, but very, very doable. But I did want to point out to you that even though in the last problem it sure looked like nice symmetry for cylindrical, and it was easy to set up, the spherical actually was easier to use, and that shouldn't surprise us when there's this sphere involved. All right, so last example in this video series for 12.7, I want us to set up a triple integral, this guy, and notice that we're not integrating 1 anymore, so you can't interpret this triple integral as volume. This is actually going to be hypervolume. Just to reiterate, I tried to hammer this hard in 12.5, hypervolume is not some abstract, useless, made-up concept. You can interpret hypervolume as useful things, like, for example, mass. So a lot of real-world phenomena are actually, technically speaking, can be written as 4-dimensional or 5-dimensional volumes and so on and so forth. So I'm not going to focus on application, but there are many, many, many situations where these kinds of triple integrals are useful and have a lot of physical, real-world meaning. So I would encourage you to pull out Google if you're curious about that at the end of this series, maybe after your homework's done. All right, so let's see if we can do it. I went ahead and tried to sketch the picture where it's bounded, volume bounded in the first octant, that's huge, by the cone. We played with this cone last time, and the cylinder and the coordinate plane. So a couple of key things to realize is that you're actually not looking for the volume inside the cone. You're looking for the volume under the cone, but inside this cylinder. So the cylinder would go all the way around and stretches on forever, but we're saying, look, only in the first octant, cut it by the coordinate plane, so here, here, and then you've got to be under this cone as well. And so you get this interesting solid, and we want to go ahead and set it up in all 3 coordinate systems. So let's look at the first one. So for part A, we'll do it in, I should probably label these. We'll do this in Cartesian. And so it's pretty easy to see that your z, well, first off, the integrand is 6 plus 4y. I'm going to go ahead and cut this as a type 1 again. It's pretty easy to see that you're going to go from z equals 0 up to the cone, and the cone we've got the formula for. So z is going from 0 to radical x squared plus y squared. So I'm going to pop a dz down. Now I've got to think about projection, but that in this problem, projection is pretty straightforward because you've got it. It's just this unit circle. It's just the corner of the unit circle right there. So you know that y, let's cut it y is going to go from 0 to the unit circle, which is the top part of the unit circle, which is radical 1 minus x squared. Technically, 1 minus x squared comes all the way around. We restrict to the right side by limiting x to go from 0 over to 1. So that's a little bit bunched together. I hope you can read the small part. Let me try to move that a little bit. And let's write this one a little bit bigger just to try to help some. Okay, so there's that one. Now let's go ahead and see if we can set it up in, I guess next we'll do cylindrical coordinates. So for cylindrical coordinates, similar initial cut. I'm going to cut this thing with respect parallel to the z-axis. First, though, I guess I better plug in everything. So I'm going to get 6 plus 4. Y becomes r sine theta, all times an r, dz, dr, d theta. So you can push that r through if you want. I left it there. What's happening? Well, you can actually take your bounds and the first one and just change x squared plus y squared to r squared if you want to, but you can also see it. Z is going from 0 to the cone, and the cone is just z equals r. Let's please realize that. The cone here is the same as z equals r. I talked about that in the last video, so I won't hammer that here. And then you just want to capture this little part of the unit circle in polar, so really easy. R goes from 0 to 1. Theta goes from 0 to just pi halves in this case. We're going to swing just up to pi halves. There's those dump trucks again. I don't know if you can hear it or not. Let's see. Let's look at, finally, spherical coordinates. And so let's go ahead and set it up as best we can. There is a little interesting part we're going to have to think about. So what happens to my integrand? Well, I get 6 plus 4. Y we learned was rho sine phi sine theta. Then I've got to multiply by a rho squared sine phi. Then I'm going to get a d rho d phi d theta. And so some of you are looking at that thinking, oh my goodness. Yeah, it doesn't look very nice, I admit. I probably am going to try not to pick this one. I'm thinking cylindrical is what I'm guessing. But still, for good practice, let's set it up. So there is a bit of a trick on this one, and I want you to see it with me. When we look up, let's actually maybe copy this 3D picture down where we can look at it down here. When I'm looking at this, I've got to figure out what rho is doing. And rho, it's funny, it's not constant anymore. If you're here, then it's going to be all the way out, whatever that value is. But when you're down here, it's just 1. Does that make sense? So it's 1, but then it's changing along here. Your distance away from the origin is changing depending on where you are, depending on the angle. It actually depends on, not on theta, but it depends on this phi. I'm thinking about the outside surface, right? So I'm starting at 0. Of course, rho is changing, right? I'm starting at 0 and I'm coming out. But I want to go from 0 out to the outside of this surface. And so I want you to realize that rho does depend very much on phi. How far down do you swing? So let me try and show you how we can see this thing. Here's what's happening. You've got the side of the cylinder, and this is distance 1 away. And then you've got the top up here as well. All right, and I'm just picking some random little point, but I don't have to be, I don't have to be on the cone. Here's the actual cone. So I'm going to pick a point right there, and my question for you is, how do you figure out what this phi is all the way down? So phi is going all the way from here to there. Does that make sense? So what angle is that? Starting at 0, swinging down. And the key to realize is you've got a triangle here. The bottom is 1. Does that make sense? And then this distance right here is rho. That's what rho is, and we're just trying to figure out what rho is in terms of phi. And so all of a sudden, I can see that, hey, sine of phi is 1 over rho. And so that means that rho is the cosecant of phi. And so this rho, my distance from the origin to wherever I am, you can be 0 sitting at the origin, you can come out, and rho actually changes. It goes from 0 all the way out to, at most, cosecant of whatever your phi is. That one's a little tricky. If you're having trouble with that, pause the video and make sure that you can see how this is different from past examples and what's going on. Now let's think about phi. So what's phi doing? Well, phi is actually starting at whatever angle this cone is. We learned last time that angle is pi 4, so I won't redo that. I'm starting at pi 4, then I'm swinging all the way down to the plane, which is pi half. So phi goes, I'm going to switch colors. Phi goes from pi fourths to pi halves. And then what's my theta doing? It's the same theta as cylindrical. It's swinging around this way from, I should label this as the x-axis, the y-axis. It's swinging from 0 around all the way to the y-axis, so 0 to pi halves. So I won't evaluate this integral with you, but I would definitely work out part B. Let's write that. So B, cylindrical, seems the easiest, and it turns out that when you work it out, you're going to get pi plus 1, and so that's your second official, unofficial homework, is to please evaluate part B and work it out. All right, well, we're done with 12.7. We've actually finished chapter 12. Great job. Give yourself a high five. High five somebody in your family that you're staying with randomly, and just if they ask you why, because you finished chapter 12, that's exciting. I'll be posting information about a brief, not a very long, a brief take-home project for exam 3. We're going to be diving into chapter 13 as well. I'll have all the due dates and things posted online on Teams very, very shortly. I am going to try not to make anything due over Easter weekend. So I might make it due, I think Tuesday, I believe is the plan. Maybe Monday, but I think Tuesday. And if you have time, I would highly encourage you to keep plugging away. When you see the schedule, you'll see the homework schedule. It's going to be tight for the next week or so. We got to get this exam in. But I'm not going to try not to force you to have anything due over Easter. Do encourage you guys to take some time and just reflect on the death of Christ and the resurrection of Christ and what that means for us today. All right,